Hello everybody, welcome to our new lecture. In this lecture, we will conclude our discussion on generative adversarial network and then we'll start our discussion on semantic segmentation. We have already started discussing about generative adversarial network. We have studied its basic version. We have studied the conditional version, and then we extended the conditional version further to discuss peaks to peaks and eventually cycle GAN. Now let us continue the discussion further. So the version that we are seeing in the slides here is the LSGAN, least squares GAN, where we are saying that instead of using the usual log loss for adversarial training, we could rather use a variant where we are introducing these preterms A, B and C, and we see that our discriminators output we are encouraging to be either similar or dissimilar to those ABC, right? Now take a moment to think about this. What would be the ideal value of this ABC according to the equations that we have written here? The first equation is with respect to the discriminator, right? And what we see is that the DGZ, this is the discriminator's output on a synthetic input, and DX is the discriminator's output on real input. Now think from the perspective of discriminator, what would be ideal value for A and B? As you would have guessed, a possible choice of parameters here would be A is equal to 0, B is equal to 1. If that is the case, then now think about from the generator's perspective, what would be the possible value for C? You already know how on synthetic, so DGZ again, discriminator applied on the synthetic data, how the generator and the discriminator, they are at a game, right? So in that case, as you would have guessed already, the value for the C will be the opposite for the value for the A, right? that is C will be equal to 1 in this case. Moving forward, let us think a bit about, can we use the components of a trained generative adversarial network for some sort of transfer learning. So let us try to understand this question better. What was GAN for? We said that the GAN was for synthetic data generation, right? Or even conditioned synthetic data generation, right? Like let's say conditioned on the domain A, data generation of the domain B, conditioned on a summer image, data generation of the winter image, as we had seen in the case of peaks to peaks, or in the case of cycle GAN. However, the question that we are asking ourselves at this point of time is that, is this the only possible use that we can generate image for a particular domain? Or maybe we could use this as some kind of transfer learning or some kind of feature extraction, and the answer turns out to be yes, this can be done. There are several works showing the potential of both generator and discriminator in different contexts, used as later as a feature extractor or for some sort of transfer learning. Here is one example which we will quickly touch upon for now. Where the SAR to optical conversion using cycle GAN. So this, like given a SAR image, the generator A, as you would have guessed, is a generator for conversion from SAR to optical image, right? And the generator B is the generator for conversion from optical to SAR image. Now, once this training has been done, the particular work that is cited below, there it was shown that this generator, now you can take it out, okay, and you can now use this as an effective feature extractor for SAR images. Which generator would you take out? We said that we are interested in feature extraction for SAR images, right? So we'll take out the generator A. Okay, so with this, our discussion on GAN we have completed for now. However, we will come back to GAN in different contexts later when we talk about different sensors. So right now we will move ahead to discuss about semantic segmentation. Before discussing about semantic segmentation, or rather to set the context, about discussing semantic segmentation, let us take a moment to recap what we already know about image classification. In image classification, in a way, the goal is to predict the dominant object category that is present in the image, right? So given an image, let's say there is a building, but there might be some vehicle parked next to the building. There might be some tree also next to the building. I'm talking about, let's say, some aerial image. And naturally, if you had to give just one label to this image, you'd give the label as building, right? So this produce one label per image. This usually doesn't provide location information. So this is useful to get a coarse understanding of an input scene. Whereas what happens in the case of segmentation, here we get much better understanding of all the present objects in the image. We get understanding of the object shapes which are missing when we are talking about just giving one label for the entire image. And this is a quite natural choice in many Earth observation talks, as quite often, like even talking about that building example, we would be interested, not just building, we would be interested, let's say, like the road next to the building. Even if, okay, like depending on the application, maybe we are not interested in the vehicles. There could be application where we are also interested in the vehicle, but even if not vehicle, naturally we'd be interested in the road, we'd be interested in the trees, right? So this is much more useful for effective understanding of a given scene. So in the semantic segmentation, we usually assign a semantic label to every pixel. Pixels of the same class, they share the same label. So the output, this is dense prediction map. Each pixel usually belongs to exactly one category. There might be cases where you could reformulate the problem in a different way and you could assign more than one category, but in most cases, the assumption would be that each pixel belongs to one category. Here are a few example semantic segmentation classes like building, road, as we were discussing the example already, right? Water, tree. Now, think about coarse resolution images, right? Like in the case of Earth observation, most of the time we are dealing with coarse resolution, 10 meter per pixel, or even like something like 1 meter per pixel. Even in that case, what would happen is that many of these classes possibly could not be a class in a, like if you were giving like for a particular, let's say we are talking about urban scenes only, and urban scenes, they're like rarely it would happen that the road is so big that this is the dominant class in the entire given image, right? So many of these would not be possibly a class if we were talking about image classification, in the sense that assigning just one label to the entire image, right? The segmentation in the earth observation has many applications, including the land cover mapping, urban area extraction. Let's say you want to work with a problem where you want to do a binary kind of understanding between which pixels belong to urban area, which pixels belong to non-urban area. Even then, especially in the boundary between the urban and the non-urban area, it would be more effective to have formulated this problem as a segmentation problem rather than a classification problem, right? This is even more prominent when we talk about flood monitoring. Let's say flood monitoring in the urban context, where there may be some alleys which are flooded, the next alley is probably not flooded due to complexity of the spatial arrangement. Or the disaster monitoring, where some of the buildings are impacted by a disaster and some other buildings are not impacted. So there, most of the times, it makes much more sense to formulate such problems as semantic segmentation problem instead of a mere classification problem. The same goes for change detection. So again, so we can connect this discussion again, like for easier understanding, to the disaster. So some disaster happened, and this means changes happened, and this, like, some of the buildings are impacted, right? And the next building is probably not impacted. So you'd try to formulate this as generally as a semantic segmentation problem, right? The key difference between change detection and semantic segmentation is that, okay, most of the times when we say we are dealing with a semantic segmentation problem, we automatically assume that, okay, we are talking about one input image. Whereas when we say that, okay, we are talking about change detection problem, we assume that we are working with two images instead of one image. So we'll be discussing in this course later, we'll be discussing change detection in much more details. However, at this point of time, it's important to understand that change detection, this is also in a way a semantic segmentation problem. So the semantic segmentation, this is a dense prediction problem, which means the predictions for each pixel, as we mentioned already. However, this also implies that the output size would be larger compared to what we have in the case of image classification. One very important point which we will emphasize again and again in today's lecture or even the next lecture is that the context plays a major role in case of semantic segmentation. How and why the context matters in semantic segmentation? A small image patch often do not uniquely identify an object. The same texture can belong to different categories. However, context is what helps us interpret between such ambiguous regions The neighboring objects often provide the semantic clues, and large receptive fields improve our understanding. Think of this way, very simple example. Just because the color observed is green, and often the texture will also be similar, it could be a green turf in a hockey field. It could be also a green color of water in some water body. So receptive field is what, large receptive field is what, or the contextual information, the neighboring objects is what will help us in understanding what object we are actually dealing with in such cases. So here is another example. The example is between road versus building wall. The horizontal gray surface near cars, this is likely a road, whereas the vertical gray surface along with windows is likely a building, right? So again, the same point emphasized that the spatial arrangement and the context, this provides us very important cues. So let us again emphasize what is important in such problem is context. To emphasize this better, let us tell this in a bit different way. What is important is not just context, it's also very important context at multiple scales. Let us emphasize this even a bit more. What is important is not just context at multiple scales, but also the global context. So we will see some methods in the next couple of lectures where the context at multiple scales is captured reasonably. For global context, in true sense, we will need to wait till much later in this course. Okay, so let us again think about the challenges in semantic segmentation. The challenges are introduced in form of large variation in the object size, in form of occlusion and clutter. Often we would see only a part of the object. So this can be much easily visualized from an example in the road driving scenario. Let's say you are driving a car and a camera is fitted in front of your car, or you are in a self-driving car. Your car, this can see the next car, the car in front of you. However, in front of that car, let's say there is a small truck, and maybe your car's camera doesn't see that truck fully, it just sees a bit of it. So the rest of the truck is occluded. But that does it mean that this is not an object of interest? This is certainly an object of interest from the self-driving scenario. So ideally, in a semantic segmentation task, we should be able to also identify those pixels belonging to the truck as truck. The challenge comes also in the form of similar appearance across classes. That could be also illumination variation. Okay, now let us move slowly to discuss about the approaches for segmentation or semantic segmentation. The early approaches, they used handcrafted features. They used shallow classifiers on the top of those handcrafted features. And often they used some kind of post-processing to improve the smoothness of the segmentation boundaries. And the performance of those early approaches was quite limited on complex scenes. Then we have already studied that from early 2010s, with the rise of the deep learning and the CNNs improved the image classification dramatically. This enabled learning of hierarchical visual features automatically. This enabled end-to-end training and reduced dependency on the handcrafted features. The CNNs for image classification eventually inspired CNNs tailored for semantic segmentation. How will slowly start unfolding towards that direction. So let us think about a typical CNN pipeline. In a typical CNN pipeline, the input image enters and are processed using the convolution layers. The features become progressively abstract. Pooling helps indeed in making these features progressively abstract, which is also very important. Pooling reduces the spatial resolution. Finally, the fully connected layers are used to predict the labels. And this kind of pipeline is, of course, designed for classification. Now, what happens with such classification CNNs? The final spatial information is lost due to the use of fully connected layers. And hence, this is not suitable for pixel-wise prediction. Segmentation indeed requires spatial reconstruction, which is missing in this classification CNNs. Whereas for pixel-wise prediction, it requires the preservation of spatial structure. Feature maps must somehow retain local information. The output must resemble an image-sized label map. How can we do that? Let us discuss that in the next lecture. Thank you.